Space, the final frontier, an infinite expanse of nearly nothing, yet somehow containing everything. This being the case, things are very, very, very far away in space. An example, our nearest stellar neighbor, aka the star that is closest to our own, is one named Proxima Centauri, at about 4.25 light years away. You may think, well, 4.25 light years doesn't sound like a lot. It's only 4.25 of whatever the heck a light year is, right? And I've seen Star Wars, and those guys gotta be doing light years by the second, so not that far, right? A light year is literally defined as the distance light can travel in a year. To rephrase that, if you moved at the speed of light for a year, that is how far you would have moved in total. 1 light year. So again, you may think, well, okay, the speed of light, now that does sound like a bit more of a significant figure, especially for a year. But I'm sure we could just kind of do it if we had enough energy or fuel in a rocket, right? Okay, I won't play the loud, incorrect buzzer sound effect again, but that's a big no-no. The reason why is, at first, an energy problem. To move mass, you have to use energy. And to move mass faster, you have to use even more energy. But a lot more energy. The reason this is the case is that mass does not scale with velocity for energy requirement. The basic kinetic energy formula is 1/2 mv squared equals kinetic energy. So if you want to move faster, kinetic energy goes up exponentially. That being the case, we can calculate approximately how much kinetic energy would be required to travel close to the speed of light. Let's start off small at about 0.1% the speed of light, so about 1,000th the speed of light. If we're trying to send ourselves on a space exploration mission, we can assume that the mass is about that of a space rocket, so about 2 million kilograms, or 4.4 million pounds. Plugging in all the numbers yields us with 1.8 times 10 to the 17th joules of energy. For all the unscientific inclined, that's a 1 and an 8 followed by 16 zeros joules worth of energy. Joule being the unit of measurement for energy. All that energy for a single second of travel at that speed. This is a joule per second, if you will, which is called a watt. So we need something that generates 1.8 times 10 to the 17th watts to travel at that speed. Well, an immediate thought is nuclear reactors, man. Solve energy with the fusing and splitting of atoms. Why not? Well, it is a lot. It's about 1 billion watts that a nuclear power plant generates. But that means we would need to strap, give or take, 180 million nuclear power plants to that rocket to get to that energy requirement. So, yeah, that's not exactly possible. Well, that being the case, why not solar energy? Not as powerful as nuclear with respect for concentration, but if we were to harness all of the energy from the sun that reaches the Earth, and I mean if we were to wrap the entire planet in 100% effective solar panels, all channeled somehow directly into that rocket, we would have about 4.4 times 10 to the 16th watts. So about halfway there to powering that rocket to travel at, again, only 0.1% the speed of light. Although, as technology improves, we will be able to get closer and closer to that number. But there remains a number that we will never be able to reach. That is, of course, 1C. C being the best number of all because it's a letter. Just kidding. C is the symbol for the speed of light, and it is not possible for matter to attain that speed. Why? Why can't I just throw a crap ton of energy at some rock in the future and get it to travel at or above the speed of light? Special relativity. Thank you, Sir Mr. Albert Einstein, often described as the greatest mind in physics since Isaac Newton, brought with him the discovery of special relativity. Now, this being a video and not a full-length college class where I can go over every facet of relativity, I'll break it down quite simply for you. Einstein suggested the idea of a reference frame. A reference frame is defined as a point you are observing from. This point can be moving through space compared to another observer, however, to you it appears as if everything else is moving. For example, you are in your own reference frame when you are accelerating in your car and you see yourself as stationary and the rest of the world is moving around you. With this idea, if two reference frames are not stationary relative to each other, time and space are viewed differently in each reference frame. On top of this, though, Einstein said that the speed of light is constant no matter what reference frame it is in, and no matter what reference frame you measure it from. These two ideas cover the fundamental aspect of special relativity, but more importantly, they give basis to the idea that mass becomes relative as well. As an object moves closer to the speed of light, its mass will actually start increasing to where an object with mass would have infinite mass when moving at the speed of light. Therefore, it actually becomes impossible to get an object with mass to move at the speed of light. And the speed of light gains a second name I find to be much funnier as the speed limit of the universe. That being the case, speeding up a rocket to light speed will never be possible. However, let me get even more theoretical with you here. Wormholes. Now you may be saying, Josh, isn't a wormhole just Space Trek Wars thingy? And I'd say back to you, first, it's Star Trek, and second, only maybe. To clarify, from what we know about physics currently, the existence of a wormhole could be possible. And such a thing would allow one to traverse through the fabric of space-time into another location or time, or both. Now, as we do not have any research on wormholes, since we have yet to verify their existence, we don't know very much about any travel through them. But we do know that it would be very likely very dangerous, as they could be subject to sudden collapse, expose you to vast amounts of radiation, and create danger of contacting exotic matter. Exotic matter being a bit of a blanket term given to matter with unnatural properties. Needless to say, if you, something comprised of normal matter, came into contact with something that was comprised of exotic matter, the result may not be very pretty. Or you may get superpowers. Maybe. Regardless, though, the possibilities of long-distance space travel have yet to be fully realized. And as we improve upon current technology and invent new ones along with develop our understanding of the universe, I'm hopeful of a world where I can go on vacation on one of Jupiter's moons.